Okay, I want you to picture a scenario. It's Monday morning.
Hmm?
You haven't had your coffee yet. You walk up to a door.
Yeah.
It's an action you've done maybe 10,000 times. You have a very clear internal rule for this.
Hmm.
You push the door, it opens. Simple cause and effect.
Push leads to open. It's probably the most basic interaction with physics we even think about. We just take it for granted.
Right. But now, imagine you walk up to that same door, you apply the same force, you push,
Oh.
and nothing.
Uh-oh.
You push harder. Still nothing. Instead of walking through, you're just staring at a solid piece of wood. Why?
Yeah.
Because the door's locked.
The locked variable has just entered the chat.
Exactly. Now, for you or me, that's just a momentary annoyance, right? We find a key. But for an artificial intelligence trying to learn how the world works, that moment is catastrophic.
It really is. It totally breaks their model of reality.
Because think about it. The action was the same push. The object was the same door. But the result just flipped 180 degrees. The rule push leads to open didn't just fail, it vanished.
And that gets us right to the core problem we're talking about today.
The problem of open-ended worlds. We're digging into a really fascinating paper called Curious Causality-Seeking Agents in Open-Ended Worlds by Zhao and his team. It's a deep dive into how we stop building AI that just memorizes patterns and start building AI that acts more like a little scientist poking the world to figure out the hidden rules.
And crucially, figuring out when those rules change.
So let's start with the status quo. We talk a lot about world models in AI. Can you give us the quick refresher on what a world model is even supposed to do?
Sure. A world model is basically the AI's internal simulation of reality. It's how it predicts the future. If I do action A, what happens next? It's what lets an agent plan ahead.
Okay. But the paper argues that the traditional way we build these models, it has a fatal flaw. They assume what's the term? A uniform causal graph.
That's the one, yeah. It basically means they assume the rules of the game are constant. Think of Newton's laws. They work everywhere all the time. They're uniform.
And traditional AI just assumes all rules are like that.
Exactly, which is fine for a game of chess. The rules of chess don't, change on Tuesdays.
Right. But the real world is messy. The paper mentions this idea of the observational window.
Yes, that an AI agent usually only sees this tiny little slice of time and space.
So, back to our door. If the AI spends a week watching people walk through an unlocked door, it learns a very, very strong rule. Push equals open.
It becomes its universal law. But then someone locks it. Now the AI sees people pushing and nothing. A uniform model, it tries to average these two realities.
It tries to find the midpoint between open and stay closed.
You got it. It thinks, well, maybe it's 50-50. Maybe it's random. It gets completely confused because it can't grasp that there's a hidden switch, the lock, that fundamentally changes the physics of the situation.
The paper has this great phrase for it, the illusion of shifting causal relationships. I found that really striking.
It is. The idea is that the real laws of physics might be constant, but from the agent's limited view, the rules look like they're always changing. The whole causal structure seems to be shifting.
So if the problem is that the AI is trying to use one rule book for a world that has multiple contexts, I guess the solution is to give it more rule books.
In a nutshell, yes, that's the metacausal graph, or MCG. That's the big contribution of this paper.
Okay, let's unpack that. The MCG. How is it different?
Well, instead of one giant, messy graph, the MCG is a collection of smaller causal subgraphs. Think of them as mini rulebooks. You have rulebook A for an unlocked door and rulebook B for a locked door.
That seems intuitive. But how does it know which book to read? The AI doesn't see a little sign that says locked.
That is the clever part. They introduce this hidden variable, a latent variable, called the metastate.
Latent, so it's not something it can directly observe in the data stream.
Right, it has to be inferred. The metastate is like a switchboard operator. It looks at the situation and says, okay, we are in metastate 1, and it routes all decisions through subgraph 1. Then something in the environment changes.
And the metastate just clicks over to state 2.
And boom, the AI is suddenly using a completely different set of causal rules. It doesn't average them anymore. It understands that context determines causality.
That feels like a huge leap. Instead of the world is chaotic, it's more like the world has different modes.
Precisely. It learns when the rules change, not just what they are.
But that brings up a huge challenge. You said the metastate is hidden. If I'm an AI just looking at a video of a door, How do I even know that a hidden state exists in the first place?
And this is where we have to shift from the model to the agent. The paper isn't just about a new model. It's about a curious causality-seeking agent. Passive observation is not going to cut it here.
Is this the classic correlation doesn't imply causation problem?
It's closely related. It's about something they call observational ambiguity. So imagine you see a rooster crow, and then right after, the sun rises. Every single day.
A followed by B. Seems like a clear connection.
To a passive observer, it might look like the rooster causes the sun to rise. You can't tell which way the causal arrow points just by watching. To find the truth, you have to do something a passive observer can't. You have to. Well, the classic example is you have to get rid of the rooster.
That took a dark turn. Or maybe just, muzzle the rooster.
Fair enough. You silence the rooster, and if the sun still rises, you've broken the ambiguity. You've proven there was no causal link. In causal theory, we call this performing an intervention, or using the do operator.
The do operator. I've seen that Judea Pearl's work. It's the difference between just seeing something happen and actively doing it.
Yes. And the agent in this paper is built to do that. It doesn't just wait for data. It generates its own data by poking the world.
So it walks up to the door and just pushes it, specifically to see what will happen.
It's a bit more targeted than that. I mean, the world is huge. You can't just poke everything randomly. That's where the curiosity part comes in. The agent needs to prioritize what it pokes.
So how do you program curiosity? Is it just random exploration?
No, it's all math. They use a metric called edge entropy.
Edge entropy. Okay, break that down.
So imagine a graph. The edge is the connection between two things, like pushing and door opening. If the AI is 99% certain that pushing opens the door, the entropy on that edge is super low. It's boring. No new information to get there.
So it ignores it.
It ignores it.
Yeah.
But then it hits the locked door, it pushes, nothing happens. Suddenly, its prediction model is all over the place. Is it 50-50, 30-70? The uncertainty spikes. That's high entropy.
And high entropy means a high curiosity reward.
Exactly. The system is designed to be drawn to that uncertainty. It sees the confusion and basically says, I need to go investigate that connection. So it prioritizes intervening on that specific action.
That is remarkably human. It's like the toddler, right? They don't play with the toy they understand. They're obsessed with the box they can't figure out how to open.
It's a very similar idea. The agent has these 3 jobs. 1, identify that hidden metastates exist. 2, map out the causal rules inside each of those states. And 3, keep refining that map by hunting for things it doesn't understand.
It's a continuous loop of hypothesis testing. I think the world works this way. Oh, wait, that was weird. Let me poke it again.
And by doing that, it breaks the observational ambiguity. It figures out that the only way to explain the data is to assume there are at least 2 different states locked and unlocked, and it separates them.
Okay, I want to get to the experiments because they sound like little video game puzzles. But before that, there's a section on theoretical guarantees. Now, usually that's where my eyes glaze over. But you flagged this as being really important.
It is, because it answers the big question. Is the AI actually learning the truth, or is it just making up a complicated story that happens to fit the data?
Right. Just because the model works doesn't mean it reflects reality.
So the authors provide a proof for something called identifiability. They show that, yeah, the agent will eventually find the true causal structure of the world. But there's this really interesting catch, a concept called swap label equivalence.
Swap label equivalence. That sounds like jargon for calling a rose by any other name.
That is exactly what it is. So let's say the real world has state A unlocked and state B locked. The AI discovers these 2 states, but it labels them state 1 and state 2. Maybe it calls locked state 1 and unlocked state 2.
So the names are swapped compared to how we would define them.
Right. But the proof shows that the mapping and the logic are mathematically identical. The AI state 1 functions exactly like the real world's locked state. We don't care what it calls it, as long as it gets the structure right.
That makes sense. But what about complexity? The AI has to guess how many hidden states there are, right?
It does, and that brings up overparameterization. It's a big fear in AI. What if there are only 2 real states, but the AI assumes there are 10?
I'd assume it makes a mess. It starts inventing imaginary rules for 8 states that don't exist.
Do you think so? It's classic overfitting. But the paper proves this architecture is robust to that. If you tell it to look for 10 states, but only 2 exist, it will just create redundant copies.
Redundant copies?
Yeah, it'll learn that state 1, state 2, and state 3 all have the exact same rulebook.
Yeah.
They become functional clones of each other.
So it doesn't break the logic. It just has a few extra keys on its keychain that all open the same door.
Exactly. And that's huge for usability. It means we don't have to know exactly how complex the world is beforehand. We can tell it, assume there could be 20 contexts, and it'll safely just collapse down to the real number.
That feels way safer. Okay, let's see this in action. The chemical task.
Right, the chemical task.
Yeah.
This was all about testing structural changes. Imagine you have 10 objects that can change color, and the goal is to predict how the colors spread.
Like a virus spreading in a network.
Pretty much. But the twist is, the rules of the spread depend on the color of one specific root object.
So if the root is blue, the rules are one way, but if it's red, they're completely different.
Yes. They tested a fork versus a chain. In one metastate, the root acts like a fork. It changes color and causes 5 neighbors to change all at once. One to many.
And the chain.
One causes another, which causes another. A domino effect.
Structurally, those are totally different graphs. One's a starburst, the other's a line.
And the metacausal graph nailed it. It figured out when the root was blue, used the fork rulebook. When it was red, used the chain rulebook. The standard models, the GNNs, they just couldn't do it.
What happened to them?
They just tried to find one structure to explain both, so they ended up with this messy web with weak connections everywhere, another muddy average.
Okay, then they ramp it up with the magnetic robot arm. This one feels much closer to a real-world problem.
It does. You've got a robot arm, a box, and a ball. Standard physics. You push the box, it moves.
It's simple enough.
But there's a hidden rule. Magnetism. If, and only if, both the box and the ball are colored red, they become magnetic.
Whoa, so if I push the red box, the red ball magically follows it, even without being touched.
Right, but if the box is blue and the ball is red, nothing. Both blue. Nothing.
That's so tricky because color usually has nothing to do with physics, like mass or momentum. The AI has to connect a visual property to a physical law.
And not just any visual property, a specific combination. A standard AI would push the box, see the ball move sometimes and not others, and probably just conclude the ball is, glitchy or random.
It wouldn't think to check the color.
But the curious agent did. It noticed its confusion score, that entropy spiked whenever things were red. It thought, wait, my predictions only fail when these objects are red.
So it started intervening. It probably just started painting things red on purpose to see what would happen.
Effectively, yes. By doing that, it isolated the magnetism metastate. It learned the rule pushbox causes move ball only exists in that very specific context.
And they tested this under tough conditions.
Oh, yeah. They added noise, corrupted the data, even blocked the AI's view of some objects. But because the MCG understood the underlying mechanic, not just the pixels, it maintained really high accuracy.
This feels like a major step toward robots that can actually function in our world.
It really is. I mean, think about autonomous driving. That is the ultimate open-ended world.
Sure. The rules of the road are consistent, but not always.
Right. Usually green light causes go, but what if a police officer is standing in the intersection holding up their hand?
The context shifts. The officer metastate overrides the traffic light subgraph.
Exactly. A standard pattern matching AI might really struggle there. It sees green, it wants to go. A metacausal AI would recognize, oh, I'm in the human directing traffic state. The rule green means go is off. The new rule is follow hand signals.
That is a safety-critical difference. It's not just about being smart. It's about not causing an accident.
It's about understanding how the data was generated, not just what it looks like. It's the difference between memorizing the answers for a test and actually understanding the subject.
But there's always a but. The paper mentioned a limitation around reachability that I found kind of philosophical.
Ah, yes, interventional reachability.
Sounds like a term from sci-fi.
It's a constraint on learning. The agent needs to poke the world to learn. But the paper admits, what if there are states you just cannot cause?
An example.
Let's go back to the door. If the door is locked and you don't have the key and you can't pick the lock, you can never, ever enter the unlocked metastate.
No matter how curious I am, I can push on that door for 1,000 years.
And since you can never witness it opening, you can never learn the causal rule push leads to open. To you, that rule effectively doesn't exist. It's a blind spot.
It's a fascinating limitation. It implies that truth is limited by your agency. If you can't interact with it, you can't understand it.
Which is pretty true for us humans too, isn't it?
That's exactly what I was thinking. So we've moved from this rigid view of the world to a metacausal one where context is everything. And we've seen that you need to be a curious, poking agent to find the real truth.
And that even if the world is messy, the math can help us sort it out, as long as we can actually reach the buttons to press.
Which leaves me with a final thought for you. The paper admits that an AI can only learn the laws. For states, it can physically trigger.
Right. It hits a hard wall of ignorance.
So, does that mean there are fundamental causal laws of our own universe that we or any AI can never discover? Not because we aren't smart enough, but simply because we lack the physical ability to trigger the necessary metastate.
Like the physics inside a black hole or some
Right.
other dimension we can't interact with.
Exactly. We might just be pushing on a locked door, building our entire theory of the universe on locked physics, totally unaware that if we just had the key, the laws of nature might look completely different.
That's a humbling thought. We could just be living in one subgraph of a much, much bigger reality.
Something to mull over. Thanks for listening to this deep dive into curious agents and the nature of causality. We'll see you in the next context.
See you there.